Okay, so in this video lecture, we're going to discuss solution of system of linear equations using MATLAB. One of the main uses of matrices and vectors is in solving system of linear equations. So for example, okay, these three linear equations can be represented by the following matrix form. No? So you have the coefficient matrix A, and then the column of variable X, and then the column of constants B. Okay, so we go to solve the linear system. We're going to use the following commands. Okay, we want to determine the sum of the diagonal entities. Now we use the trace function. So RREF will transform the augmented matrix AB into the reduced echelon form. And note that when A is non-singular, a square matrix, then the augmented matrix will contain the identity matrix and the solution to the equation. So LinSolve also solve the linear system AX equals B provided that A is non-singular, and then the number of non-zero rows of a matrix can be determined using the rank command or function, and then the spec will compute the eigenvalues of a square matrix. The rank will determine the number of non-zero rows of a matrix. The solution for the linear system AX equals B by the Cramer's rule is applicable only when the coefficient matrix is a non-singular square matrix where the determinant of A is not equal to 0. Okay, so given AX equals B, so A is a coefficient matrix, okay, X is the column of vector, and then B is the column of constant. Okay, so we're going to use the determinant to determine x1, x2, xn. And then we define first your matrices A1, A2, and so on. A is a coefficient matrix. Now, note that A1 is obtained by, is the matrix obtained from A by replacing the column or the x column or the x1 column by the column of constants. Example. So you're given the system of linear equation. Okay. So define first your coefficient matrix. Then get the determinant. Okay. So note that the everything that is written after the double slash is will be considered as comments in MATLAB. Okay, for A1, we replace the first column by the column of constants. No? So this is okay. So there's a correction here. Okay, so this has to be 0. Okay, so 901. And then solve for x1 using determinant of A1 over determinant of A. Then in a similar manner, we obtain x2 and x3. Okay, for solution by matrix inverse, given AX equals B, if A is non-singular or the determinant is not 0, then your solution X is equal to the inverse of A, coefficient matrix, multiplied by the column of constants. Okay, so defining your A. Okay, and then your B. Okay, and then we compute. Okay, we can compute for solution, for the solution X, by just typing inverse of A multiplied by B. And then that gives you the solution, okay, for x1, x2, and x3. Using LinSolve, if A is non-singular again, we can use, so this is a direct method of finding the solution. So you just need to define your A, okay? After defining A and then your B, so just type in solve AB, and then that gives you the solution to x1, x2, x3 using lean solve. And then by Gauss-Jordan reduction method, okay, this is a method. Remember that in your linear algebra, this transforms the augmented matrix AB to the echelon form by performing row operations on matrix A. So in MATLAB, define first your AB, okay, your augmented matrix. But you don't need to put the semicolon, no? So just write down the entries of A as the last column of the augmented matrix AB. So the method is applicable for all types of solution: consistent, distinct and multiple, and then inconsistent. So you can also use this when A is singular. So when A is singular, it means that the solution will be dependent. Okay, the solution will be dependent. So solve the linear system of the previous problem using RREF. Okay, so we write down your AB. This is the augmented matrix. So the last column will be the column of constants. And then we just, okay, type RREF AB. Okay, and then that will give you the reduced echelon form. Okay, since A is non-singular, you have the first three columns here as the identity matrix, and then the last column will be the solution, okay, for your x1, x2, and x3. Okay, so that ends my